All right, guys, so today we're going to talk about gas stoichiometry. And you guys know how to use the ideal gas law, and you know stoichiometry, and today we're going to put them together. Before we do that, though, we're going to do some very basic gas stoichiometry where we're just converting between two gases. So you should have read about this and already attempted 3 problems from the assignment that was given in class. So and I'm going to go through one of those with you in just a second. So if you didn't get those or didn't quite understand the reading, hopefully it'll make sense to you after this. So the first thing we have to understand is it's easy to convert between two gases because gases, no matter the identity, a mole of any gas occupies the same amount of space. Okay, and that's a very important thing to understand. Liquids and solids don't work that way because liquids and solids are so dense that larger particles result in a mole of those particles taking up more space. So for example, if I have, let's say a crystal that's made up of 6 atoms, very small crystal, but let's say this is aluminum, and these are relatively small atoms. And over here, I have, let's say, some gold atoms. Well, they're going to be a lot larger. So if I have a half dozen gold atoms, they're going to take up more space, right? So this volume over here of aluminum is much smaller than this volume of gold because the individual particles of gold are larger. Well, with gases, it doesn't matter because with gases, the particle size doesn't matter because really the particle size is so small compared to this space between the particles. So let's go to a little PhET thing real quick and show you what I'm talking about. So if I put, let's say, 50 heavy gas particles in one of these and 50 light ones in the other, okay, and the light ones are moving faster, the heavy ones are moving slower at the same temperature, 300 kelvins, but they're going to occupy the same space. Because again, if you look at the space, I'll just pause one of these for a second. Even these big guys here, the size of the particles is so much smaller than the space between them. And of course, in a real gas sample, the size of the particles would be much, much smaller even than this compared to the space between them. So unlike in a solid or a liquid, the size of the particles really doesn't matter. So if I show you this real quickly here, we're going to allow the volume to change, and we're going to hold the pressure constant. And what I'm going to do is just, I'm going to add a couple of light particles here, and I'm going to put the width on to show you how wide this little box is. So right now the width of the box is 10 nanometers. And because this is a two-dimensional picture, let me unpause this. Because this is a two-dimensional picture, the width basically substitutes for the volume. So each box right now has 50 particles, right? This one 50 light ones, this one 50 heavy ones. And they're both the same volume, right? And again, we're substituting volume with width because the other dimensions would be the same. So even though the light particles are smaller, they don't take up any less space because they are a gas, all right? A mole of any gas occupies the same space. 50 molecules or particles of any gas occupies the same space regardless of the identity of the gas. Okay, so let's say I bump this up to 60. All right, so 60 light particles now has a width of 12 nanometers. It got a little bit bigger as we would expect. But if I do the same thing to the large particles, bump them up to 60, again, exactly the same. So it doesn't matter the identity of the gas. The volume of a mole of any gas is the same at a given temperature and pressure. If we change the temperature and pressure, things could change. But if they're both at the same temperature and pressure, then they're going to occupy the same volume. Okay, so because of that, when I look at a balanced equation that has gases in it, this 2:1:2 ratio of these 3 gases is not only a molecule and a mole ratio, but it's also a liter ratio, okay? So what that means is I can say that 2 liters of hydrogen would react with 1 liter of oxygen to produce 2 liters of water vapor, okay? As long as they're all gases, we can say that. We could change it to milliliters, you know, it doesn't really matter. It's just a ratio. So 2 milliliters of hydrogen, 1 milliliter of oxygen would result in 2 milliliters of water vapor, right? So, and of course, we can still consider them to be moles and molecules if we need to, but you'll see that it's helpful to see them as volumes as well. So let's take a look at one of the problems that you were supposed to have attempted on the homework. This was number 38. How many liters of propane gas will undergo complete combustion with 34 liters of oxygen gas? So first of all, you need a balanced equation, and this was actually given to you in the text, but I'll go ahead and rewrite it here. Okay, and this is going to make CO2 plus H2O. All right, and so this one, let's see, we had 3 and we had 4, and that gave us 10 oxygens, so we put a 5 there. Okay, so there's our balanced equation, okay? So how many liters of propane gas, and the propane is this stuff, C3H8, will undergo complete combustion with 34 liters of oxygen gas? All right. So all that means is I'm going to start with 34.0 liters of O2, and I want to convert that to liters of propane, C3H8. Now, normally when we think about liters, we might think about using the ideal gas law. But because both of these substances are gases, we don't have to do that. We can just use the balanced equation. So I'll show you what I mean there. So I can go from liters of oxygen to liters of C3H8, just like that. And the ratio comes from the balanced equation. There's an implied 1 in front of propane. So I'm going to put a 1 there in front of liters. And there is a 5 in front of oxygen. So I'm going to put a 5 there. And so that's going to give me 1/5 ratio. So I've got, let me grab my calculator here, 34 divided by 5, which should give me my answer. Oops, made everything go away. That's all right. 34 divided by 5, 6.8 was our answer there. This back. All right, so 6.8. Oh, started to say moles, that's wrong. Liters, right, of C3H8. And that is how you do a liter to liter conversion using a balanced equation as long as they are both gases. And so that's how you were supposed to have done those 3 problems from the homework. Okay. All right, so let's take a look. What if, and of course you need to write this down, this is your notes. What if we are instead dealing with something that's a solid or a liquid? So pause the video, write down the example question and everything, and we'll work through it. Okay, so how many grams of magnesium would be needed to react with 20 liters of oxygen at 1 atmosphere and 30 degrees Celsius? So this is a little different because I'm talking about magnesium, which is a solid. So my other substance is oxygen, and that is a gas. But in order for me to say that I have like a 2-to-1 liter ratio, they would have to both be gases. And since magnesium is not a gas, we're not going to be able to do what we just did. Okay, they have to both be gases in order for it to be a simple one-step liter to liter conversion. Okay, so what can we do? Well, we can plan the problem out. And this problem is asking us for grams of magnesium, right? And it's giving us liters of oxygen along with pressure and temperature. But the main thing is it's giving us liters, okay? So how can we kind of bridge that gap between liters of oxygen and grams of magnesium? So the first question is, how do I get to grams of magnesium? The unit I would need first, or just prior to getting grams of magnesium, would be moles of it, right? And just like any stoichiometry problem, to get moles of one thing, I can get that from moles of another. And in this case, it's going to be moles of oxygen, because that's the other substance mentioned in the problem. The question is, how do I get from liters to moles of oxygen? And the answer is using not only the liters, but also the pressure and the temperature, because oxygen is a gas. Okay. So in other words, we're going to use the ideal gas law for this part. Then we're going to use stoichiometry to do the last two steps. Okay. So I'll show you what I mean. I'm going to use the ideal gas law first. So we're going to start with, we're looking for, we're looking to go from liters of oxygen to moles of oxygen. So I'm trying to solve for moles of oxygen. So I take PV equals nRT, right? And of course, N is moles. So to get N by itself, I would rearrange and I would get N equals PV over RT. We've done lots and lots of that sort of rearranging, right? Okay. Now, this is moles of oxygen. I probably want to note that, and it'll become apparent here in just a minute why it's important that I note that. But I'm going to put a little subscript O2 on my end, just to remind me that it's oxygen that I'm finding. Okay, so the pressure in this case is right at 1 atmosphere. The volume, well, the volume is 20 liters. Oops. R is always the same down here on the bottom, right? 0.0821. And the temperature is 30 kelvins, but we have to add 273. So that's going to be 303 kelvins. Sorry, I said 30 kelvins. I meant 30 degrees Celsius. Add 273 to get it to kelvins. Okay. So now let's figure out our moles. So we go to the calculator, clear out our last answer. And 1 times 20, of course, is just 20. So I'm going to say 20 divided by, and then in parentheses on the bottom, 0.0821 times 303, close the parentheses, then hit equals, and I get 0.80, I'm going to call that 0.804. And that would be moles. Now, be very careful here. We have two substances in the problem. We have oxygen that we're given the liters of, and we have magnesium that we're trying to go to the grams of, right? So which one did I just find? Right, I just found oxygen, right? That's why I labeled it back here. So make sure you label that, moles of O2. And the reason that's important is if you don't label it oxygen, you might think that you're already here. You're already at moles of magnesium, but you're not. You're back here. And so it's going to mess up your math potentially. And in this case, it definitely would. Okay, so let's go ahead and do that conversion then. So we're going to do 0.804. The rest is just stoichiometry, which we should be very familiar with. 0.804 moles of oxygen, the answer we just got. We're going to convert from moles of oxygen to moles of magnesium. Why? Because that's our plan. And of course, that's going to allow us then to go to grams of magnesium, right? The moles of magnesium from the balanced equation, looks like we've got a 2. Oxygen is a 1. Moles of oxygen goes away. And now I've got moles of magnesium to grams of magnesium. And this part you're very familiar with. We just go to the periodic table. Magnesium is 24.31 from the periodic table. And I'm just going to leave the number in my calculator that I already had. I don't even have to round it at all. So because it's right here. So I'm just going to multiply by 2. And then also multiply by 24.31. All right, I got 39.1. I think 3 sig figs is what I want. Yeah, 39.1 sounds good. and that is grams of magnesium. Tough to do a mental check again, unless you've done lots and lots of these reactions. Yeah, so that looks good. Let's try one more, and then I'll turn you loose to do some problems. You can always, of course, come back and watch the video if you need help, going into doing some stoichiometry problems on your own, if it's helpful to you. Okay, so this time it's a little different. It says how many liters of hydrogen gas, so my goal is actually liters of gas, would you expect to produce by reacting 28 grams of aluminum with excess HCl at 21 degrees Celsius and 762 mmHg? So from liters of hydrogen, I'm also given information about aluminum, right? I'm given grams of aluminum over here. So how do we bridge that gap? Well, an easy thing to do would be go out from grams of aluminum. I'm pretty much definitely going to go to moles of aluminum, and then probably to moles of hydrogen, right? So then the question is, do we go directly from moles of hydrogen to liters of hydrogen? Well, if hydrogen is a gas, and I know the temperature and pressure, and I believe I do, then I should be able to do that last part using the ideal gas law, right? Okay. So let's go ahead and do this first part using stoichiometry. 28.0 grams of aluminum, and it's reacting with excess HCl, so we don't have to worry about the HCl. Aluminum is our limiting. Okay, so my first step is going to be to go to moles of aluminum, right? So do that first. Periodic table tells me 26.98 grams of Al per 1 mole. And then we're trying to get to moles of hydrogen. So that's going to go on the top of the next step. And of course, moles of Al goes in the bottom because that's what I'm trying to get rid of. And it looks like our balanced equation, we have 2 moles of Al for every 6 moles of, sorry, that was HCl. Yeah, we're not talking about HCl, we're talking about H2. My bad. So 3 moles of H2, there we go. Okay, and I'm going to stop there because I'm going to need the ideal gas law to do the last part, to go from moles of hydrogen to liters, right? Okay, so we're going to do 28 divided by 26.98 times 3 over 2. 28 divided by 26.98 times 3 divided by 2. And we get 1.5, I'll just call that 1.5, I guess 1.56 for the time being, ought to work. Okay. And again, make sure we're careful about labeling that. That's moles of hydrogen. And now we want to get to liters of hydrogen. That's our end point. So that means we're going to take the ideal gas law, namely V equals nRT over P. Okay, we just found our N, 1.56, R, 0.0821. And our temperature, we have 21 degrees Celsius, so plus 273, maybe 294 kelvins. And then on the bottom, our pressure up here is in millimeters of mercury. So we're going to do a little side calculation here. So 762 mmHg, we're going to have to take to atmospheres. Okay, and 1 atmosphere is 760 mmHg. So it's going to be very close to 1 atmosphere, but let's just see. 762 divided by 760, 1.00, we'll call it 1.003. Why not? Okay. So 1.003 atmospheres. All right. Calculating time. So I've got 1.56. Yeah, make this thing smaller. This is ridiculous. There we go. 1.56 times 0.0821 times 294 divided by 1.003 gives me a volume of 37.5 liters. There you go. That's it. That's gas stoichiometry. So we'll get a chance to do some reactions next week after getting a little bit more practice with this. But again, you can always rewatch these if you need a little refresher as you're doing some of the problems. But yeah, make sure you show all your work, and you'll have a few problems to do. So good luck, and I will take your questions on Monday. Thanks, guys.